Okay, so now in this section, we're going to go over the physiological web of vascular disease. And basically, what we're doing is we're going to go into more of an upstream mechanism of things that cause vascular disease. In the vascular pathophysiology, we're really more downstream. So things like vascular endothelial dysfunction and injury, and endothelium permeability, and oxidation of LDL, and atheromas, and hypertensive changes. Those are all the things that are happening downstream. And sometimes you need to immediately go into downstream and have an effect. And other times you have time to go more upstream. And upstream is really where things like the gut play a role, and there's hormone imbalances may play a role. And your determination of whether you go upstream or downstream could be based on several factors. One of them could be how serious the situation is versus how much time you have. So as an example, if you had someone with the same amount of clinical examination findings, let's say that were abnormal, and let's say they had some hypertension, and they had some chronic venous insufficiency and some abnormal lipid particles, and homocysteine was a little bit high. And if their coronary calcium score was 1200 versus someone's who was 0, you would have more time with the one that was 0 to go upstream than the one that was downstream. So downstream one, you may do some immediate interventions, like try to figure out how to get their blood pressure down right away. Whereas with someone else, you might go, hey, maybe there's a relationship between some of their symptoms, like maybe their gut function and their blood pressure and lipid panel, and maybe you give yourself a few months to go and address those upstream mechanisms. Okay, so the goal of this presentation academically is to understand the physiological interactions that impact vascular health. And the clinical goal is to understand the relationships with upstream mechanisms that impact vascular health. And here's the web. And the key areas we want to focus on is the GI tract, thyroid reproductive hormones, adipocytes, insulin, and the brain. So let's start with the GI tract. So we look at the GI tract, and we look at the research being published now. What we're seeing is things like the gut microbiome have a huge impact on mechanisms we never thought before, like blood pressure. So bacteria release different types of mediators that have a huge impact on the renin and angiotensin system. And we also know that our genes can make us more vulnerable for different changes of different microbiome species. Some of us will have a greater sensitivity to salt. Some of us will have a greater sensitivity to salt when our microbiome changes. Some of us will have less sensitivity to salt as our microbiome changes. But the combination of environmental factors and diet and changes in the microbiome all really play this dynamic role in blood pressure, and we'll go over the specifics later. But this is very fascinating because this is published in Nature Reviews in Cardiology, which is, a very formal, strict journal, and they are always cutting edge when it comes to the sciences of where trends are happening. And then when you look at some of these papers being published in the top cardiology journals, there's this explosion of research where they're looking at the impact of the microbiome and its impact on atherosclerosis and blood pressure, and even looking at things like probiotics, prebiotics, and things they can do, even fecal transplants and other types of research where they're looking at cardiovascular links with the gastrointestinal tract. Now, one of the greatest areas of discovery in recent years was the production of trimethylamine oxide, or TMAO. And what they found was that for certain people with various microbiomes and different clearance of these metabolites, that foods that are really high in L-carnitine, choline, and lecithin, for example, red meat and eggs, can be metabolized by different bacterial species to TMA, trimethylamine. And then trimethylamine is converted in the liver by FMAOR into TMAO, or trimethylamine oxide. And TMAO oxide is destructive on the vascular endothelium. It destroys the vascular endothelium. And there's some strong links between cardiovascular disease. And when this discovery first started, they started to go, okay, well, this may be why some people can't handle eating red meat all the time. Or this is why there's an increased risk for red meat consumers. It may not be everyone, and maybe the reason it's not everyone is because there's different bacteria species in different populations. And for some populations, when they eat these foods, like really high in choline, like eggs and red meat, their bacteria may be the deciding factor whether it actually causes destruction of their arteries or not. And for some people, their TMAO levels go up, and some people it doesn't. So this is first like big aha moment of the gut microbiome and how it really has a role in cardiovascular disease. And since then, there's been an extensive amount of study on TMAO And now they've linked elevated TMAO levels. And by the way, you can measure them. So we're going to talk about doing laboratory tests later. And one of the markers we're going to measure is serum TMAO. And serum TMAO levels that are elevated definitely have a relationship to thrombosis and embolisms, vascular injury, atherosclerosis, even directly to heart failure and injury of the glomeruli and kidney disease and fibrosis as well. So this is something that is promoted by a combination of dietary precursors and different bacterial species in the gut. And here you can see another study where they really show the relationships of phosphatidylcholine and choline from diet being converted by the gut bacteria to TMA, and then TMA being converted to TMO and then TMAO, and then showing that this relationship between atherosclerosis and heart failure. And here you can also see some of those illustrations as well with different bacterial species and then TMAO effects. And they've also found that TMAO promotes type 2 diabetes. It also impacts insulin receptor signaling. It also increases metabolic syndrome pathways through different disruptions of signaling pathways. So it's not just heart disease, but also some of the other factors that contribute to heart disease as an independent factor, risk factor. And here you can see, again, another illustration of these protein-rich foods, high in carnitine, phosphatidylcholine, metabolized to TMA, metabolized in the gut to TMA, and then the liver converts to TMAO, and then this destroys the vascular arteries. And then this illustration, you can see different bacterial species. These are the bacterial species. They have identified the bacterial species. But, people always ask, well, can't you just take a probiotic? Can't you just get rid of these bacterial species? Can't you do a panel? Not yet. If you guys do your comprehensive digestive stool analysis, they're not measuring these bacterial species. We're not there yet, even in the functional medicine world, to look at these bacterial species. We just have to look at the TMAO levels directly and see if any of these mechanisms are taking place. And for the most part, all these bacterial species haven't also been all discovered. There's only a few of them that have been discovered. So it's not like you can just change the bacterial species by taking a probiotic and these things change. So that's a question that people always ask. So there are definitely things you can do, and we'll talk about it, changing the microbiome to change the TMAO levels. But there are specific species that contain the TMA lyse enzyme, and the TMA lyse enzyme is what converts choline to TMA. And then once that TMA is formed, it gets converted and oxidized by a oxygenase enzyme into TMAO oxide, which is very destructive. And then when you look at this slide here with the gut microbiota and TMAO also, in addition to causing insulin resistance and damaging the vascular endothelium, also directly causes platelet hyperactivity. So it does promote clotting and those types of reactions as well. So, you can look at these links between gut microbiota, TMAO, and it does directly cause that foam cell formation to take place because it's a free radical. And it does increase messenger proteins that cause hyperresponsiveness for clots. So the risk for not only vascular injury destruction of the endothelium takes place, but also for thrombus and emboli formation that take place. And it actually does directly injure cardiac tissue that causes fibrosis. So it's a very inflammatory, toxic compound. And here you can see the same thing, TMAO levels, and it shows that within the blood vessels, TMA level elevations increase inflammatory responses like NFKB, adhesion proteins, inflammasomes. They decrease nitric oxide. They increase platelets. They impact macrophage foam cells. They promote those formations, leading to atherosclerosis, heart failure, heart injury. They can injure the glomeruli and even cause renal artery stenosis as well. So these are the different bacterial species that contain the TMA lyse enzyme that convert foods like eggs and red meat that are high in choline into these TMAO compounds. And when you look at these different strains of bacteria, there's multiple strains, and these strains all have different effects with each other. And it's not just like one is high and that's the one that's causing it. It's a combination of all these different relationships together. And when you look at the human microbiome project, what they really identified is there's no such thing as a good bacteria or bad bacteria, and there's no single effect of one bacteria. It's how these bacteria integrate with each other that then determines functions. So the simple model of finding the bacteria is bad and trying to kill it and then trying to give a good probiotic does not work. That's like a very simplistic model, and everything coming out of the Human Microbiome Project showing that it's not that linear when it comes to the microbiome, and it's not that linear when it comes to TMAO. So this is another illustration of important pathways. Here you see TMAO, increasing inflammatory mediators that cause platelet hyperactivity. And what they're trying to illustrate in this diagram is that in combination with like insulin resistance and a high-fat diet, smoking, obesity, other risk factors can really be a deadly combination, right? With cardiovascular disease, you're trying to reduce your risk, but TMAO is an independent risk versus very unrelated to these other risk factors as well. And then when you look at studies like this one, where they looked at the relationship between plasma levels of TMAO and all-cause mortality in stable cardiac patients, you can see the higher their TMAO levels were, the higher their mortality, the higher of death, and this link to all-cause mortality. So, you know, TMAO levels are, again, something that we definitely want to keep down. So in a clinical setting, you're going to measure TMAO levels. And if you see them elevated, then you get to figure out, okay, what do we do? Well, let's talk about diet. And let's talk about things that impact TMAO from a dietary perspective. So should they be off all red meat? Should they be off all eggs? Should they be off all choline? Should they take choline supplements? What are the key factors there? So this is a study where they looked at the impact of chronic dietary red meat, white meat, or non-meat protein on TMAO metabolism and renal excretion in healthy men and women. And chronic dietary red meat increased systemic TMAO levels, and discontinuation of dietary red meat reduced plasma TMAO levels within 4 weeks. So there are definitely relationships between foods high in choline that once this mechanism is in place, and it's not for everyone. Like, listen, everyone in the world doesn't have high TMA-laced bacteria in their gut that causes these reactions. Some people do, some people don't. We don't have a tool to measure those bacterial species. All we can really measure is TMAO, and if it's high, then we know that their consumption of higher choline foods can be a factor. Now, it's not just red meat. So fish and whole grain cereals also are very high in choline, and they can also increase TMAO. So this was a study that was conducted, and they go, in conclusion, this study demonstrated that diets rich in fish or in whole grain cereals significantly increase plasma TMAO. These changes mirrored the baseline association between higher TMAO concentration, higher intakes of fish and whole grain products, suggesting that plasma TMAO mainly reflects dietary intake of these healthy foods, and therefore it's not a universally valid biomarker of cardiometabolic risk independent of background and diet. So, you know, foods that could be very healthy for us, for certain bacterial species, can really create an inflammatory free radical. And, you know, eggs actually have been shown in studies, and I'll show you some meta-analysis when we talk about diet tomorrow, to be cardioprotective. And they actually even reduce the risk of stroke. But for those that have that choline-rich egg yolk, that may be something that increases their TMA levels. And fish, who doesn't encourage healthy amounts of fish for people that have cardiovascular disease? Well, for people that have these different changes in their microbiome, it can be a problem. Same with those that promote whole grain and high fiber for cardiovascular disease. So this goes again to, like, it can't just be about, well, I eat healthy food and I take supplements so I don't have any risk for cardiovascular disease. What if you ate fish all the time? What if you were on the Mediterranean diet? What if you were eating lots of healthy fibers with choline in there? And you check your choline calcium score for the first time in your life, and you find out you were severely compromised. So again, you have to do the evaluation. You have to assess, because there's these variables we don't think about that we even know about that occur. Now, this was a study where they looked at the Mediterranean diet. The Mediterranean diet is supposed to be great for us. They looked at the Mediterranean diet on TMAO levels, and they go, these results suggest that broad dietary pattern, Mediterranean diet intervention over 6 months may not be sufficient for reducing TMAO concentrations in an otherwise healthy populations. Disruption of the conversion of dietary TMA to TMAO should be the focus of future studies. And this is why it's so important. Because if you get fixated on a diet and go, hey, a large study, meta-analysis study confirmed the Mediterranean diet reduces cardiovascular disease. So as long as you're eating healthy amounts of fish, high in choline, and olive oil, and high fibers, high in choline, then you should be okay. Well, not necessarily. This is where personalized medicine comes in. So if you look at the general population, maybe the entire general population doesn't have this TMAO level issue. But so when they put them on a Mediterranean diet, it has more protective effects for more people. The signal is that it's protective in a large trial, in a large study. But there's individual outliers in which this Mediterranean diet can actually even potentially increase their TMAO levels because it's so high in fish. So this is the reality of where diet, nutrition, and lifestyle come into cardiovascular medicine. Individual uniqueness, individual changes that are important to look at. This was a paper, and they looked at among generally healthy adults, contrasting plant with animal intake. While it kept over dietary components similar to plant products, improved several cardiovascular risk markers, including TMAO levels. There's no adverse effect on risk factors for plant products. So this is from a randomized clinical trial where they took a bunch of people on a plant-based diet, then put them on an animal-based diet. They took a bunch of people on an animal-based diet and then put them on a plant-based diet to see what would happen. So it's that typical crossover trial. So here you can see people on a plant-based diet, and they put them on a high animal-based diet, and then you can look at their TMAO levels. They didn't change that much. There's some significant change in some of the population size, but not that much. Now, look at the animal product eating diet, high animal product, compared to plant, and look at their TMAO levels drop significantly. Now, you have to understand, these people here that are eating high plants have a different microbiome than these people. Like heavy meat eaters compared to heavy people that have a plant-based diet have different microbiomes. People that have more of a plant-based diet typically have a more diverse microbiome. So for them, even going to an animal product didn't cause much change. But for those that consumed a lot of animal products, when they converted to a plant-based diet, their TMAO levels significantly were reduced. You can see that different in these spaghetti platter plots here. Plant-based diet, you're looking at different TMAO levels, and they go to plant, not much level change in TMAO. Animal-based people, diet, high TMAO levels, they go to plant, and there's a significant reduction there. So they found these TMAO levels definitely differ from these different groups, and weight also was a factor, and LDL cholesterol also tended to change too. So when you look at, for example, LDL cholesterol, plant-based diet, once they went to animal, their LDL cholesterol did go up. Then once they went back to plant, or animal went to plant, there was a drop of 10-degree LDL cholesterol. So there are some influences on some people, microbiome, in which really a high plant-based diet, low animal protein diet can make a big difference for them. But again, this is not for everyone. Not everyone has these different types of mechanisms. This is the individual uniqueness of different people. And then what they also looked at here was the influence of other confounders like sodium intake between one group or another. And what they found was there was no difference in sodium intake in these studies between the animal and plant-based groups. And then if you look at saturated fat, big difference in saturated fat with the animal-based groups. And saturated fat is really what's raising their LDL levels. And then their fiber intake was much, much higher in the plant-based group than the meat product group. So there's some changes and differences in saturated fat and fiber between these two groups that may have made some of these differences. Now, what about nutraceuticals? So the bottom line is with TMAO is like if you actually have high TMAO levels, there could be some impact of dietary rich foods and choline like red meat and fish and cereals that are high in choline to increase TMAO levels. Well, what about nutraceuticals? Well, probiotics have no effect. So probiotics have no effect on TMAO levels in human clinical trials. Several of them have been done and completely useless. Now, on the other hand, natural phenols, polyphenols, totally different story. Really powerful effect. So here, this paper makes a statement that natural polyphenols as a bioactive compound with many promising beneficial effects on human disease development are reported to regulate gut microbiota composition, hence may serve as new agents in TMAO-enhanced atherosclerosis, and they do. And specifically, resveratrol has been shown to do this. So to our best of our knowledge, we have demonstrated for the first time that resveratrol attenuated TMAO-induced atherosclerosis by regulating the synthesis of TMAO and bile acids via remodeling the gut microbiota, and that resveratrol-mediated hepatic bile acid neosynthesis was partially modulated by downregulating the gut liver FXR, FG1F access, or these are receptors in the gut. So you can see here resveratrol coming in, and then you can see things that are listed in purple are down regulations, and things in green are up regulation. So resveratrol has a significant impact in how bile acids are metabolized by cholesterol, which has protective effects. But resveratrol also has this ability to downregulate the TMA lyase in gut flora. So there's less TMA produced, eventually leading to less TMA. AS stands for atherosclerosis. So resveratrol directly impacts the gut flora and has an impact on those TMA producing pathways. Other studies have found TMB. So a structural analog of choline 3,3-dimethyl L1-butamine DMB is shown to non-lethally inhibit TMO formation from cultural microbes, to inhibit distinct microbial TMA lyases, and both to inhibit TMO production from physiologic polymicrobial cultures to reduce TMO levels in mice fed at high choline and L-carnitine diet. And DMP is something that's found in things like olive oil and grapeseed oil and balsamic vinegar. But DMB directly impacts these TMA lyse enzymes like resveratrol, so the total TMA level goes down. So in addition to resveratrol with TMO levels, we really want to consider having people that have high TMO levels increase their consumption of extra virgin olive oil, balsamic vinegar, and grapeseed oil to raise their total DMB exposure to the gut microbiome. Berberine is also another compound that has been shown to have effects. So berberine was shown to inhibit choline to TMA conversion in TMA-producing bacteria in vitro and in gut microbial consortium from fecal samples of choline-fed mice and human volunteers. So berberine also has this direct effect on these TMA lysenzyme bacteria in the gut, and it lowers the TMA levels as well. And also hawthorn extract is the last one. So this present study indicated that hawthorn fruit extract was able to reduce TMAO exacerbated atherogenesis by attenuating inflammation by improving antioxidant capacity, at least in mice. So resveratrol, which we use all the time in cardiovascular disease because it has protections for the vascular wall. Berberine, which we use all the time in vascular disease because it has a very, very powerful insulin signaling agent compound for those that are insulin resistant. And then olive oil we use all the time because of its anti-inflammatory properties. So some of these foods we use for cardiovascular disease indirectly are impacting these TMAO levels also. And one of the things that we want to talk about is in our clinical workup, we want to, once we identify TMAO levels, we may want to consider these nutraceuticals as part of our intervention in addition to diet. Now, when we look at lifestyle for TMAO, we can see some interesting things. So this was done with caloric restriction and exercise, the effects of lifestyle interventions on plasma, TMAO, and obese adults. And what they found was the primary finding of the study is that caloric restriction combined with exercise promoted a reduction in TMAO, while a eucaloric diet, which means they eat the exact amount of calories they have for their energy demands, combined with exercise, promoted a modest increase in the smallest size cohort of obese insulin-resistant individuals. So basically, they found caloric restriction reduced their TMAO levels. Exercise wasn't necessarily really a factor there. And they also found the change in TMAO after intervention was inversely correlated with baseline visceral adipose tissue. So there's some relationships with body fat as well. Here you can see the average levels of change. Hypocaloric, you can see this dotted line. There's an average reduction in TMAO by about 30%. And with the eucaloric, it actually went up. So exercise, which could be a free radical without caloric restriction, in this one study subgroup may be a factor. The other very interesting thing is sleep. And in this study, they looked at different metabolites during sleep deprivation of 24 hours, and they found TMO levels went off the charts with sleep deprivation. So sleep is critical to keep TMO levels under control. And then here they show that it's possible that TMAO is neither a causative nor protecting factor, but maybe merely disrupted homeostasis. Now remember, TMAO, anything the body makes, isn't always bad. So if TMAO levels go up too much, they can cause injury because it's a free radical. But also TMAO, being a free radical, can neutralize infections, has these pro-oxidant activities that we really need. So it really is about balance. The best way to kind of know what balance is just to see if it's totally outside of a normal population range, is what the lab is measuring. So when you look at TMAO, they point out that it has some impacts throughout the body, and TMAO levels is about liver metabolism, about the diet, and how quickly things can be excreted, the different bacterial species there in the gut, and it may be harmful or not harmful based on how all these factors are involved. Now, here's a summary of these major steps, and then we'll go into uh, the application of this in a real life setting. So here you see fatty foods, choline, L-carnitine, and being metabolized by enzymes in the gut that are high in TMA-lase. And then TMA is produced. TMA goes into portal circulation, and liver enzymes, FMAO and FMAO3, they're mono oxygenases. They will convert TMA to TMAO. And then in addition to choline and carnitine fatty foods, cold water, deep seafood fish high in choline also contribute to this pathway. And then once TMO is made, if it accumulates and the levels get high, then that can lead to platelet aggravation, macrophages from cell activation start to cause vascular injury, and those are all factors. But another big part of this is how TMO levels are cleared. If you're making TMAO and you're clearing it, you may end up with normal levels and they don't have elevations. Now, in this diagram here, you can look at diet, lifestyle, and exercise. They all impact microbiome modification, and they can impact different microbiome metabolites that impact vascular health. It's a combination of clearance and production that are really involved with these bile acids. Let me give you some outcomes with TMAO. So let's say you have a scenario where a person has high consumption of fatty foods and or cold water fish. So lots of precursors. They have a healthy microbiome. They have healthy renal clearance of TMAO. So despite eating lots of fatty foods and high fish, they have normal TMAO levels. And that's the large portion of the population. Not everyone has this TMAO mechanism. But I will tell you, from someone who's been measuring TMAO levels a lot the past year, a lot of people have high TMAO levels. So it's not a rare finding to see it abnormal. And I'm going to show you some case studies of people with high TMAO levels later. Okay, here's another scenario. High consumption of fatty foods and fish, high choline foods, dysbiosis. They have healthy renal clearance, and they may have elevated or normal TMAO levels based on how quickly they can clear it, even though they have the bacterial species in particular that are causing these shifts. Here's another scenario. High consumption of fatty foods and or cold water fish, healthy microbiome, but they have impaired renal clearance. So they may have elevated levels really because of impaired renal clearance. And here's another scenario. Normal consumption of fatty fish and cold water fish. Microbiome genes for TMAO production with unhealthy diet. They have the genetic susceptibility there. They have healthy renal clearance and the combination of genes, but healthy renal function may make their TMAO levels normal or they can't clear it quickly enough, so it's elevated. So these are all the possibilities. So it's diet plus the microbiome plus renal clearance that really determines TMAO levels. Now, if you do a summary of what's been published on TMAO, you can see this chart that goes over all the findings. So this is a chart that I put together called Variables Associated with TMAO Levels. So what's been shown to increase TMAO levels in the literature so far is gastric bypass surgery. Gastric bypass surgery immediately changes the microbiome, and for whatever reason, TMAO lyse bacteria go up and TMAO levels go up. Sleep deprivation. Pregnancy has been shown to increase TMAO levels. Toxic chemicals have been shown to increase TMAO levels. High-fat diet with dysbiosis or reduced clearance. Cold water fish consumption with decreased clearance. L-carnitine with dysbiosis, decreased clearance. Red meats, egg, dairy products with high levels of choline, carnitine, and less than have all been shown to impact TMAO levels. Now, TMAO levels can be reduced with vegetarian diet, vegan diet, Mediterranean diet, assuming it's not too high in fish, high fiber diet, vitamin D and B vitamins, resveratrol, D&B and olive oil, balsamic vinegar, grapeseed oil, and meldonium, which is an anti-ischemic medication, has been shown to lower TMAO levels. Now, once a person has their TMAO levels go up, that's where you have these different changes throughout the body. The cardiovascular system, you get just basic injury to the vascular endothelium and to the heart tissue itself. Insulin resistance develops. You get increased inflammation and altered insulin receptor signaling. You get kidney damage. You get systemic inflammation that turns on NFKB, so the whole body becomes inflamed. There's also increased TMO levels that have associations with malignancies, specifically colon cancer and prostate cancer, and can also directly induce liver damage. So that's TMAO. Really interesting, really fascinating stuff. So when we do a cardiovascular workup, you're going to see one of the markers we're going to check will be serum TMAO levels. And that's all the background information on it. Now, there's other gut metabolites besides TMAO that you should be aware of. So one of them is phenylacetylglutamine, PAG. And unhealthy gut microbiome patterns or dysbiosis, and even some genetic variations to people's microbiome, may impact how they metabolize general dietary proteins, not specific to any one type, where they make increased amounts of this PAG compound. And this PAG compound has been shown to bind to androgenic receptors, which will increase blood pressure, then also bind to different receptors that cause things like thrombus formation and increased stickiness of platelets. So there's some relationships between PAG producing bacteria, heart attack, and stroke. Then we also know that the microbiome is involved with different types of sulfur metabolism and sulfur processing. So for some people, they can produce different end products. And also some people with different microbiomes can respond to phytoestrogens differently. This is why people or studies done with populations of Asian cultures have different impacts of phytoestrogens for protections than American studies, because there's different microbiomes in those populations of how they eat. And then we also know that different nutraceuticals, different flavonoids may be different end products that have different effects on cellular physiology because of how these microbiome species work. So the flavonoids you take may also have a different effect on your physiology based on your pre-existing microbiome. You may do better with resveratrol, or you may do better with turmeric. Some people have a very unique difference. Some people can't tell. Most people can't tell, but sometimes it's very unique from one person to another with what they see works for them. And this is the issue with so much individual uniqueness that makes it hard to just make general protocols for people. You have to basically get into the clinical setting and see what they actually respond to. Now, in this illustration here, you can see that different gut bacteria can alter tryptophan metabolism. This can cause mood disorders. This can cause insulin resistance. This can cause inflammation. This is the IDO1 pathway that's involved. But again, these are based on different bacterial species. And then how bile acids are used in the gut also have an impact on cardiovascular disease. So bile acids that are released by the gallbladder normally go through this pathway where the liver makes gallbladder, the gallbladder contracts, bile acids are excreted, it gets into the ileum. They bind to FXR receptors. Remember, FXR receptors are receptors that control gut activity. We talked about that in the GI module. Then they get reabsorbed and taken back as secondary bile acids. But in that process, bile acids may become oxidized. Bile acids can be configured to a different shape by different bacteria in the gut. And then this has been shown to maybe have some role and impact on metabolic syndrome and insulin signaling pathways. So certain microbiomes combined with bile salts can lead to metabolic syndrome. And it goes on to show that, how important these bacterial metabolites are and how little we know about them. We're almost like playing this little game when we do this comprehensive digestive stool analysis and see these bacterial species and assume they're good or bad and try to make our protocols from it. It's just really not that simple. Now, there's also studies on looking at the gut with intestinal permeability and cardiovascular disease. And for the most part, what you see is that, once a person develops leaky gut, they get an inflammatory response, they get an inflammatory cascade, and those inflammatory cascades then have some impact on promoting coronary artery disease. And different things like short-chain fatty acids and TMA and TMAO and bile acids combined with, you can see leaky gut down here, that has this role. And the biggest concern is this endotoxemia pattern where someone has intestinal permeability and bacteria gram-negative bacteria release byproducts called lipopolysaccharides, and lipopolysaccharides get into systemic circulation. And lipopolysaccharides bind to what are called toll-like receptors. And toll-like receptors are found throughout the body, and in this scenario, they're found on immune cells, your macrophages. And they activate the inflammatory response, which then causes atherosclerosis. Intestinal permeability has also been shown to play a role in hypertension. So when there's inflammatory processes in the gut and there is this permeability response that takes place, there's some shifts that take place with different gut metabolites, and especially if there's not enough short-chain fatty acids, in which blood pressure levels can also go up. So here you can see relationships between intestinal damage that's taking place, causing these toll-like receptors to go up, systemic inflammation being promoted. These intestinal permeability patterns have also been associated with dysfunction in G-coupled proteins and short-chain fatty acid imbalances that lead to diabetes. Then you get a combination of different risk factors with intestinal permeability. And then they also show maybe there's TMAO changes, and the combination of these things then lead to cardiovascular disease. And you'll see short-chain fatty acids a lot here. We're going to talk about them. But short-chain fatty acids really come from fiber sources, and they really have a protective role when it comes to the gut and throughout the body. Now here you can see dietary factors. You can see zonoglutin toxin. This is something that causes permeability. Tight junctions break. Lipopolysaccharides get released. They get into systemic circulation, and they're going to bind to toll-like receptors and cause that inflammatory response. And here you see another illustration of the tight junctions. But what's interesting here is they're stressing out the point that high blood pressure also breaks these barriers down. We tend to think of like leaky gut only being caused by inflammatory foods or infections in the gut. But hypertension does impact the intestinal tight junctions. And these intestinal tight junctions, when they break, then create the pattern for inflammatory responses that lead to atherosclerosis. So if you have patients that have uncontrolled high blood pressure, that may be a factor why they're having their tight junctions break down. Now, as we shift from atherosclerosis more into hypertension, there's been lots of studies looking at the gut microbiota and its role in hypertensive disease. This is a review paper that goes into that. Recent evidence suggests that gut microbiota plays an important role in the development of pathogenesis of hypertension, dysbiosis, and imbalance in the composition and function of gut microbiota was shown to be associated with hypertension in both animal models and humans. Here you can see the microbiome, and you can see that there's different inflammatory mediators that are released that impact the oxidized LDL that can lead to hypertension. On the other hand, a diet that's high in fiber can increase short-chain fatty acids like butyrate, acetate, and propionate. And these short-chain fatty acids bind to G-coupled proteins. They cause vasodilation, and they can actually protect against heart disease. This kind of illustrates the point of why fiber has an impact on blood pressure. And the main reason is because these short-chain fatty acids go up. Now, you can actually supplement with short-chain fatty acids like butyrate and acetate and propionate, and also raise the total gut short-chain fatty acid level in a clinical setting as well. Now here you can see an illustration between short-chain fatty acids and TMAO, dysbiosis and salt sensitivity. They found that for certain people, their bacterial species in their gut can make them extremely sensitive to salt. And then their salt sensitivity can increase their absorption, and then their blood pressure levels can go up. So there's a few interesting things about salt. We know that when we're younger, we don't seem to be as sensitive to salt for blood pressure. And as we get older, we become much more sensitive. Now, two main mechanisms have been found that may play a role there. One is changes in the microbiome. Second one is inflammation of that glomeruli has been shown to increase salt sensitivity with individuals. Meaning, when I say salt sensitivity, I mean how they taste salt. I mean the sensitivity of salt changing their blood pressure levels. And they've actually looked at what things can actually calm that down. And acetate, propionate, and butyrate can decrease blood pressure, short-chain fatty acids from fiber. And TMAO may also have some role in vasoconstriction in addition to atherosclerosis. That may be a factor as well. So now we're looking at these models of dysbiosis-induced hypertension, where you need to have lots of short-chain fatty acids. And and healthy amounts of nitric oxide and dampen the inflammatory response to combat hypertension. And when you look at short-chain fatty acids, again, acetate, propionate, butyrate, that are made in the gut microbiome from fiber, they basically are fuel sources for the gut, but they're also signaling compounds that bind to these specific G-coupled proteins. And we know these control insulin signaling. We talked about that in the diabetes course, but they also have significant impacts on blood pressure as well. So you can see someone who's ingesting lots of dietary fiber has these short-chain fatty acid levels go up, and these short-chain fatty acids bind to these different FFAR receptors and G-coupled protein receptors, and they have an impact on blood pressure modulation and impact on inflammation as well. And here you see another illustration of that. Dietary fiber, short-chain fatty dietary fibers consumed, bacteria in the gut produce short-chain fatty acids, acetate, propionate, butyrate. These are used by fuel sources. They calm down local inflammation, but they also bind to receptors that decrease total body blood pressure. So short-chain fatty acids and TMAO can be looked at, protective and destructive properties. Another way to look at this is if TMAO levels are really high. You may also want to consider using fiber as a dietary supplement, or even increasing that fiber as a dietary strategy, and even taking short-chain fatty acids like butyrate, propionate, and propionate and acetate to make a difference there. Now, when you summarize these different steps, you can see there's a few things that take place when it comes to the gut and cardiovascular disease. So the foods we eat combined with the gut bacteria then produce these metabolites. And these metabolites may be TMA then because of TMAO that really promotes atherosclerosis. These dysbiotic changes in the bacteria can alter bile acids, and bile acids can then impact FOXR receptors and impact inflammatory responses that are pro-inflammatory in that way. Or dietary sources can increase short-chain fatty acids and actually protect the gut, and also modulate insulin signaling and then protect the system as well. Here's another summary of these different metabolites in the gut that have a role in cardiovascular disease. So TMAO, destructive, PAG, bind to androgenic receptors, increasing blood pressure, also promoting thrombosis and atherosclerosis. Short-chain fatty acids, acetate, propionate, butyrate, helping control blood pressure, homeostasis, myocardial repair, modulate inflammation. Lipopolysaccharides being released from leaky gut that cause inflammation, vascular dysfunction, vascular injury. Bile acids that bind to FXR, LXR receptors that can control lipid metabolism, insulin metabolism. And if the bile acids are oxidized, maybe even produce inflammation. And then Brecresol, S4, and doxy sulfur compounds, which have been shown to cause renal dysfunction as well. So the gut microbiome does play a role in different models of heart disease. Here's another one. It's basically illustrating the same things. Dietary fiber, raising butyrate, protective, intestinal permeability, releasing LPS, different bacterial species releasing TMAO, and then the role in cardiovascular disease through destruction of the vascular endothelium, platelet hyperactivity, or directly through muscle injury, smooth muscle injury of the heart. And this is another one that goes into a little more detail about these mechanisms as well. We see short-chain fatty acid providing energy and fuel for the gut, also having a significant anti-inflammatory effect, producing energy. Bile salts, really critical for normal function. Leaky gut, LPS being released. So it's basically those different metabolites. Now, we also know that the microbiome is impacted not only with diet, but also obesity, physical activity, and aging. So the more dysbiosis a person has, the more likely these negative effects take place. If there's dysbiosis, there's typically short-chain fatty acids that are low, and there's high amounts of inflammatory mediators that can break down tight junctions. There seems to be a relationship with more of these TMA lyse pathways and PAG metabolites that promotes inflammation, oxidative stress. So the upstream model of looking at some of these cardiovascular inflammatory markers and looking at TMAO levels and looking at blood pressure is really to look at things like physical inactivity and diet and strategies to improve the microbiome. We know that all these mechanisms get worse with age. So aging is another key factor there. But the interventions that they've been studying now in the field of cardiovascular disease medicine is exercise, dietary intervention, prebiotics. Prebiotics, probiotics don't seem to work. There's even some studies with transplants that are being done, which have mixed results, and then trying to reduce these TMAO levels. But ultimately, there's this relationship between the gut and these metabolites. Now, I summarized them here in one diagram for you, or the major ones. So you can see increased salt, decreased fiber, inflammatory foods, hormone imbalances, infections, lack of selectivity. They all cause microbiome dysfunction. And this microbiome dysfunction can lead to intestinal permeability. And the intestinal permeability, especially if there's already dysbiosis, can lead to these dysbiotic bacteria releasing these endotoxins called lipopolysaccharides into the gut, but because of the intestinal permeability, get released into the bloodstream. Then lipopolysaccharides then bind to toll-like receptors throughout different tissues in the body, even through different immune cells. That creates a systemic inflammatory response, and these things have been linked to promoting atherosclerosis. Now, dysbiosis may also cause bile acid disruption, where you have different responses of disfigured bile acid signaling agents on G-coupled proteins that then cause insulin dysregulation, cholesterol metabolism dysregulation. And then you have here dysbiosis metabolites impacting the IDO1 pathway, which involves tryptophan alterations. And these dysbiotic changes can increase what are called KYNA and KYN that then promote atherosclerosis. And here you see the other metabolite, phenylacetylglutamine, being involved with dysbiosis, also promoting inflammatory receptor responses and also binding to androgenic receptors that increase blood pressure, platelet aggregation, and increase clotting. And then TMAO we talked about, which causes vascular epithelial injury, thrombus formation, plate hyperactivity, and cardiac issues. So this is really the GI model of the web. So pretty fascinating stuff. So when you really look at these things, you got to consider how much time do you have to fix the gut? Because treating the gut is upstream. And it may take a while before you take those changes. And immediately controlling blood pressure is downstream. So if you have the time, you have the mechanisms, you may need to go after those pathways. And it's really important to measure things like TMAO as part of the clinical workup, as well as looking at intestinal permeability and things like LPS, lipopolysaccharides from leaky gut. So that's the GI connection to cardiovascular disease. Let's go into insulin. And I think this is something we all know about. But basically, hyperinsulinemia has an inflammatory response in tissues. It's just that simple. Insulin, hyperinsulinemia turns on the RAGE reaction. It turns on and impacts the mTOR gene expression pathways, creates oxidative stress. You can get free fatty acid accumulation. You get oxidized LDL. These things all start to impact cardiac tissue health itself. And then insulin resistance also decreases nitric oxide, increases reactive oxygen species, and potentially increasing advanced glycation end products. And those mechanisms of low nitric oxide and increased advanced glycation end products and free radicals directly cause hypertension and also damage the vascular endothelium, leading to atherothrombic risk. And here you can see insulin resistance increasing what's called PAI1, plasminogen activator inhibitor 1. This is a key pathway that increases fibrinogen activity. You can see platelet reactivity. And on lab testing, you can measure this as something called fibrinogen activity. If you ever see high fibrinogen activity, you always have to go back and look at insulin resistance. And when you look at insulin resistance and the effect that it has on blood vessels, it's pretty scary stuff, because not only does it destroy the vascular endothelium and cause permeability, but it actually turns on these inflammatory mediators that can really lead to unstable thrombose that lead to emboli and cause some potential concerns with embolytic strokes and embolytic-induced myocardial infarction and so forth. So insulin has an impact also on these transfer proteins. You can see insulin increasing cholesterol transfer protein. Cholesterol transfer protein levels change. And with people that are insulin resistant, these changes that take place with lipid metabolism in the liver causes LDL levels to go up, HDL levels to go down, triglyceride levels to go up. And if they're in an inflammatory state, then you can have things like oxidized LDL potentially go up. Now, typically insulin resistance doesn't cause oxidized LDL to go up unless you have severe inflammation, oxidative stress. Certainly if you see HbA1c above the 7 range, you definitely want to carefully look at that oxidized LDL. But here's just an illustration of how insulin impacts these ApoB proteins and impacts this cholesterol ester transfer protein and changes these lipids. And here you can see a diagram of insulin resistance really causing changes in calcium influx, sodium retention, endothelial dysfunction, macrophages, all leading to hypertension. It's one of the side effects of insulin resistance. And you get vasoconstrictive changes. So all the negative things that you look for can be promoted by insulin resistance. High blood pressure, high oxidized LDL. You can even see increased small LDL particle size because the total LDL levels are starting to go up. You can see inflammatory oxidative markers like CRP, homocysteine. So insulin is really upstream and can impact all the major cardiovascular risk factors and also throughout the tissues in the body. This is a really good diagram that shows insulin resistance really impacting the whole body, from everything from brain inflammation to artery injury to macrophage activity to peripheral arterial disease and resistance in blood vessels. And it's a key factor. And one of the things you have to be aware of is how this is going to pop into your office. Because one of the ways you'll see this pop into your office is a patient who comes in and says they have infertility. And when you look at the statistics, the number one cause of infertility in the United States is polycystic ovarian syndrome, where dysinsulinism increases testosterone levels. So, in this paper, they're going, listen, PCOS is going to potentially progress into cardiovascular disease. And when you see women in childbearing years where they're having infertility issues, and they're having some of these maybe cardiovascular markers like the blood pressure a little bit up and their insulin resistance is there, they're on their way to destroying their vascular endothelium and developing CVD, as well as breast cancer risk. So that's like a red flag. Because again, you're in a functional medicine practice, it's going to be pretty rare someone walks in and goes, I don't have any symptoms. That's why I'm here. I just want to spend money on doing a cardiovascular workup because I thought it would be important. Like, that doesn't happen. It doesn't happen. What typically happens is I have enough suffering to motivate me to come see someone, or I have enough concerns to come to see someone. And one of the most common things that people see practicing functional medicine is infertility. So remember, the one cause of infertility is PCOS. PCOS is linked to insulin patterns. So once you start seeing people with insulin patterns, you have to realize that a lot of the cardiovascular markers could be elevated. And even after their fertility issues are managed, you still want to look at their cardiovascular disease risk and so forth. And you may want to do a coronary calcium scan, coronary artery calcium scan with them to see what their levels of dysfunction are, especially as they get older. Now, here's a summary of the things that are happening with insulin resistance. So insulin is going to do several things. First of all, if there's advanced glycation end products, those advanced glycation end products are going to bind to receptors for advanced glycation end products called RAGE. That's going to cause a systemic inflammatory response that's linked to direct vascular endothelium damage. Insulin is going to activate fat cells. We're going to talk about that in a second. And when fat cells get activated by insulin, there is an inflammatory release of TNF-alpha IL-6, which promotes atherosclerosis. But there's also an impact on adiponectin. Adiponectin is protective, and adiponectin levels go down. So the protective mediators go down, the inflammatory markers go up in body fat. We'll talk about this more in the next part of the web. But this promotes atherosclerosis, and it can be triggered by insulin. Now, insulin has different effects on males and females. And in males, insulin will upregulate the enzyme called aromatase, and aromatase will convert testosterone to estrogen. And when men have their testosterone levels go up and estrogen goes up, that increases cardiovascular risk and atherosclerosis. And insulin promotes this PCOS pattern where it activates a 1720 lyase pathway. It's found in the thecal cells of the ovaries. It's part of the PCOS pathophysiology. And then testosterone levels go up. And testosterone levels go up in females, increases atherosclerotic risk. So we'll talk about this more as part of the web as well. Now, insulin will increase aldosterone activity, cause sodium retention, so blood pressure levels can go up. It'll alter cholesterol transfer protein and HMG co-reductase to increase total cholesterol, increase LDL, decrease HDL, alter particle size where the smaller particle numbers go up, alter apolipoproteins where the B1 levels go down, A1 levels go up. So all the things that promote atherosclerosis risk. So this is the insulin part of the web. Let's move on to adipocytes in fat tissue. Now remember, fat cells used to be thought of just storage cells. That's where we just carried excess calories. And we know that adipocytes are now also considered part of the endocrine system because adipocytes release things like leptin and TNF-alpha and adiponectin and so forth. And when you look at body fat, we have brown body fat and white body fat. And the brown body fat, we have a set amount that we're born with, and it's found like underneath our thymus gland, by our thymus, underneath our sternum, and what controls thermoregulation, but it also is very protective for us because it releases something called adiponectin. And you can measure serum adiponectin. We're going to talk about that in our workup. And adiponectin really protects everything. It calms down inflammation, protects his blood vessels, improves insulin signaling. So we want to activate that. And things like cold plunges, which become really popular these days, they actually turn on these brown cells to release adiponectin, which has these vascular dynamic effects and cardioprotective effects as well. And then you have white fat. White fat is what you accumulate when you have excess calories, not enough physical exercise. So the more body fat a person has, the more potential is for an inflammatory response. So, in theory, you want reduced amount of white fat activation, higher amounts of brown fat activation. And we'll go over strategies discussing what's been published to do that in a second. But these fat structures then release their mediators like adiponectin and TNF-alpha directly into the vascular endothelium, and then that has an impact on the vascular endothelium. So here you can see different expressions of fat cells. So here we see healthy fat cells, healthy immune function, fat cells release, they're having Treg activity. These are modulating immune function regulators, anti-inflammatory macrophage activity, adiponectin, which is very, very protective, vasoprotective, anti-inflammatory, impacts the blood vessels. Everything's healthy. Everything's nice. And here you have obesity, and you have inflammatory mediators like Th1, Th17, pro-inflammatory macrophages, churning on white fat, and white fat being different than brown fat, right? But these white fat substances then increasing leptin, reactive oxygen species, creating the inflammatory cascade, which can then start to damage blood vessels. And here you see cerebrovascular disease without obesity, meaning you don't even have to have increased body fat. But even without obesity, inflammatory mediators turn on adipocytes, which basically create the same inflammatory mechanisms and reactions. So it doesn't have to be obesity. It's just that the reactions are much more. There's more white matter, more white fat. And this is a great illustration of body fat directly impacting the vascular endothelium and promoting plaquing. And, if you look at human cadavers, I remember if you guys remember anatomy lab, but you would see these hearts and there'd be fat all around the arteries, like especially around the heart. And these fat around these arteries directly impact release of mediators into the vascular endothelium. And then they have their promoting effect of causing atherosclerosis. Here you can see it even better. You can see these fat cells here just directly releasing mediators into the smooth muscles and even to the vascular endothelium. And if there's more free radicals nitric oxide, then you get dysfunction, which you can see there. And here you see this bidirectional effect. Here's the blood vessels. Here's body fat, white body fat. inflammatory mediators being released into foam cells directly, foam cells releasing cytokines, it activates body fat, and you get this vicious cycle that's taking place. So the other key thing to remember is that once these inflammatory pathways start to show up with the vicious cycle and this feed-forward pathway of cardiovascular disease, the more body fat a person has, the faster it goes because of these intimate relationships. And this is where things like intermittent fasting may be something that has to be jumped into pretty quickly with some people that are significant risk, but just to reduce their total white body fat content. And here you can see endocrine signaling. You can see that adipocytes have a direct effect on heart function and muscle contraction. And you can see the fat surrounding cardiovascular tissue directly impacting smooth muscles, cardiomyocytes, and then impacting vascular signaling pathways. Now, this is an overview chart of positive and negative effects of different adipokines, adipokines being proteins released by body fat, these messenger pathways. And some were anti-inflammatory and some were pro-inflammatory. So adiponectin being the main one, the one that's most studied, seems to really impact coronary artery disease in a positive way and decreases infarct size, decreases blood pressure, impacts heart pressure, and these other ones being pro-inflammatory. And here you see in this chart here, which is this, put in your notes for your review, that adiponectin downregulates everything, and leptin and resistin, all things impact fibrosis and vascular injury and so forth. So they even use the term normal fat and dysfunctional fat. And the difference between normal fat and dysfunctional fat is dysfunctional fat has inflammatory triggers. See, with normal fat, you see anti-inflammatory macrophages taking place, no problem, and even with physical activity and movement and activity and just general immune function, there's an anti-inflammatory adipokine response. Dysfunctional fat, and especially if the more dysfunctional fat, the greater the inflammatory response, is when inflammatory mediators or things like insulin activate these cells, and that's when these mediators are really promoted. So the more, one of the things we'll talk about in the physical exam is looking at body mass index. And if you look at body mass index, and their body mass index is high, and they're in this cardiovascular vicious cycle, it's going to speed up everything because of these mechanisms. And it may be unrelated to their total insulin levels as well, just the body fat itself. And when you look at here, you can see body fat, and then body fat is lean, it's anti-inflammatory. Then they show the body fat increasing in size, getting more inflammatory reactions in it. So M1 is pro-inflammatory. These release inflammatory mediators. This causes vascular injury, plaque formation, atherosclerosis, and systemic inflammation throughout the body, and eventually damage to the beta cells, islet cells, diabetes, and cardiovascular disease develop. Here you're seeing body fat directly activate the renin-angiotensin system, which then promotes blood pressure changes. So it can cause hypertension. So we think of hypertension sometimes caused by body fat because there has to be all this pressure that's generated to get blood into these fat tissues throughout the body. And as a matter of fact, the more body fat a person has, the more blood vessels have to reach out to these tissues, and the greater the heart has to work to get blood flow to these tissues, so blood pressure goes up. But also, adipocytes release these inflammatory mediators, these adipokines, that impact the renin and angiotensin system that also have a change in blood pressure. And then we get into the adipokine pathway, which I want to talk to you about. And the adipokine pathway is the protective one. So this is where the adipokine pathway impacts endothelial cells and has an effect on blocking hypertension and protecting vascular injury. So I summarize this for you here, and then we'll go into clinical strategies, especially with adiponectin in a second here. So there's fat cells in the body. The more fat cells, the greater potential for these, but the person doesn't have to be fat for these fat cells to be activated. Insulin surges, sedentary lifestyle, inflammatory cytokines, and even obesity, activates these adipocytes. Adiponectin, which is protective, goes down, so there's greater insulin resistance. Apelin, resistin, bisvatin, BAP all go up. Those activate plasminogen activator inhibitor 1 that causes greater platelet activity. You can measure that with fibrinogen activity on a blood test. And then these same adaptokines increase the systemic inflammatory response, runs atherosclerosis. They actually decrease vascular endothelial growth factor 1, which is what you need for blood branching, blood vessel branching angiogenesis, which is involved with recovery. And these adipokines also decrease nitric oxide synthase directly, the enzyme, and they may even damage the vascular endothelium. So you get this promotion of heart disease in those scenarios. Now, adiponectin is one that's really, really important for us. And this is one that comes from the protective adipocyte that comes from body fat tissue. And adiponectin has impacts throughout the body, not just the blood vessels, but it helps impact brain efficiency, impacts insulin sensitivity, impacts vascular growth, and general immune function. And adiponectin levels going up have been shown to directly block these inflammatory cytokines from body fat, and also increase and enhance insulin signaling and reduce inflammatory pathways. So what has been shown to change adiponectin levels? So here's a summary. So from diet, decreasing saturated fats reduces adiponectin levels. Increasing polyunsaturated fats, like olive oil, increases adiponectin levels. Increasing fiber intake increases adiponectin levels. And caffeinated beverages increase adiponectin levels. And by the way, tomorrow I'm going to show you the large meta-analysis studies, multiple meta-analysis studies that actually show that things like coffee are actually protective for the heart and reduce stroke risk for majority of the population. There's some small variables that has the opposite effect with, like those that have severe hypertension. But you can get your adiponectin levels activated with things like coffee and fiber and olive oil and decreasing saturated fats. Exercise increases adiponectin levels. Cold plunges. Cold plunges are critical for people that have peripheral arterial disease, people that have venous insufficiency. They can have a huge impact by doing cold plunges. And these are getting more popular. You can buy these cold plunges in your house that are always on for people that do it on a daily basis, sometimes even more than once. And then reducing body fat itself increases adiponectin levels. As far as nutraceuticals go, omega-3 fatty acids have been shown to increase adiponectin levels. But the most powerful response has been with raspberry ketones. So raspberry has flavonoids, and certain flavonoids are ketones. And raspberry ketones have been shown to increase adiponectin levels, as well as grapeseed extract. So these are all things that are impacting the gray fat. So when someone has this cardiovascular mechanisms, the goal is to reduce their white fat as much as possible, reduce inflammation as much as possible, but at the same time, consider things like cold plunges and even coffee and raspberry ketones to get these adiponectin levels to have that protective response. Now, if we go from fat cells, we get and move on to the web, we get into the brain. And brain autonomics have a significant impact on the electrochemical activity of the heart, obviously because they control the AV node, SA node, and so forth. But they also have a direct impact on blood pressure and autonomics. And they can also have an effect on what's called vascular or neurogenic inflammation, where increased sympathetic activity can cause increased injury to blood vessels. So here you see neural connections from the brain to the heart. You can see the cortex is involved. The cortex activates the endocrine system, the hypothalamic pathways through endocrine hormones, but also through the adrenal glands, through autonomic pathways, descending projections to the pontomedullary reticulospinal tract, and these things impact the SA node, AV node, and you get normal cardiac function as well. And then here's just the different areas of the brain that impact brainstem areas, nucleus accusatorius, so forth, rostral, lateral medulla, where these autonomic centers are, and these control blood flow. Now, why are these important? Because there are people that have mini strokes and microvascular disease and get little infarcts throughout their brainstem, and they never have their blood pressure controlled again. That happens all the time. So you see a person who gets an MRI, they have microvascular disease, they have uncontrolled hypertension, and their uncontrolled hypertension can't be fixed with salt or potassium or various nutraceuticals that impact the nitric oxide pathways, because there's an injury to the brain that controls these sympathetic outflow centers. And there's also some of these effects that take place with stroke. So this is important to know. So here you can see that the brain actually activates these sympathetic centers, sympathetic and parasympathetic centers. And when people get brain injury, the brain injury could be from traumatic brain injury. Brain injury could be from microvascular disease, and brain injury from stroke. That there can just be brain inflammation that then impacts cardiovascular, vascular dysfunction in general. There could be injury specifically to the insular cortex, which is involved with autonomic functions. So you get dysautonomias, and you get different types of cardiac dysfunctions. The most common one being inability to gate sympathetics, because the way the brain works is that the cortex and the brain fires in a healthy state to inhibit sympathetic centers that are found in the cord. So when there's a brain injury, you don't get increased parasympathetics, you get increased sympathetic responses. And this also happens after strokes. Some people get a stroke, massive stroke, or even microvascular disease. Different areas of their brain get injured, and as their brain gets injured, they can't control their autonomics anymore. They get hypertension, they get increased amounts of catecholamines. These increased catecholamines start to impact blood pressure, but also impact just muscle cell function, where you start to get basically necrosis and injury to muscles itself. And here you can see different brain areas being activated, or even you can think of this different brain areas being injured, where you get arrhythmias and dysautonomias and different heart and different dysfunctions. So the brain is something to consider. I'm going to show you a case study in part 2 of a person who's had a traumatic brain injury and now has uncontrollable hypertension. There's no other cause for their hypertension, meaning they don't have insulin resistance, they don't have any inflammatory mediators that are involved, but it's really these mechanisms potentially from a brain injury that could be impacting it. And ideally, if you can get the brain to integrate and be healthier, you may have a chance to dampen these responses. Now, studies done on traumatic brain injuries, we went over some of these in the gastrointestinal module, shows that as soon as the brain's injured, like within hours, there's intestinal permeability. And then we know that when there is injury to the brain, in addition to intestinal permeability, within a very short period of time, within 1 or 2 days, dysbiosis develops. So what you're seeing in this illustration here is like a stroke where you have alterations in autonomic function, catecholamine levels go up, you get intestinal permeability that develops, you get endotoxemia, these lipopolysaccharides go in, you get systemic inflammatory responses called neurogenic inflammation, where the brain is can't control its sympathetics, so you get substance P releases, inflammatory mediators that then increase vascular injury and systemic inflammation, and then you get even some changes autonomically from some of these autonomic changes in the vascular system itself, where you get injury from increased sympathetic tone, increasing inflammatory mediators like substance P. The combination of all these things can then lead to cardiac dysfunction. So some people have a stroke, then they get uncontrolled blood pressure and a leaky gut pattern that becomes a vicious cycle, and then they get myocardial infarction. And you get a combination of these different mechanisms together. Here you can see, similar things here. A person ends up with a stroke, endothelial cell damage, oxidative stress. Now here they're showing after a stroke, the blood-brain barrier is opening. It's another phenomenon that takes place after stroke. So when the brain gets injured, whether it's from stroke or from forceful event like a car accident, but once the brain gets injured, those neurons that are injured have a shearing response, and there's messenger proteins to open up the blood-brain barrier, because immune cells have to come in and clear out the debris. So there's an immediate opening of the blood-brain barrier after brain injury and after stroke, and there's also opening of the gut barrier that takes place. Now, these barriers, when they open up, really set up the stage for other inflammatory mediators to come in and then really cause some significant progression of the injury to the brain. And here they're showing, like, if there's gut dysfunction and gut inflammation also, you can really create a systemic inflammatory response and then go from, stroke into cardiac dysfunction pretty quickly. And there are people that get a stroke and then get different rhythm disorders like arrhythmias. They get different types of things like atrial fibrillation right after their brain injury. That sets up the stage for embolisms and other things that take place. This is some animal studies where they induced brain injuries in mice, and these mice developed atherosclerosis right after the brain injury. So take mice, no injury to the brain. They don't see atherosclerosis development. They take mice, cause injury to the brain, and then they see these atherosclerosis developments. Apoprotein E deficient mice were more at risk because these are things that are involved with transporting proteins and lipids. But it can happen with other types of genotypes as well. So here's a summary of these mechanisms. So stroke, traumatic brain injury, or even significant neurodegeneration leads to inability for the brain to control autonomics, specifically to dampen the sympathetic response. And if it is unable to dampen the sympathetic response, then you get hypertension. And just to talk about this a little bit more, the way this works is your brain is constantly getting input from different stimuli: sound, light, proprioceptive, muscle spindle, Golgi tendon input. And these things are all increasing the frequency firing of the cortex. Well, the cortex directly fires into the brainstem. And then the brainstem directly inhibits the sympathetic centers in T1 to T12 of the spinal cord to dampen sympathetic responses. And this is why when kids are first born that haven't had their brain totally develop yet, their eyes are totally dilated and their heart rate's really, really high because they don't have that cortical development to then dampen the sympathetic response. So they end up with really high heart rates and really dilated pupils, and they're in a sympathetic dominance load. And as they walk and develop the connections in their brain starts to have greater integration, greater connectivity, which allows it to have greater ability to dampen these sympathetic inhibiting pathways to this pontomedullary response in the brainstem to dampen the sympathetic response. And then all of a sudden, you can see the pupils become more normal size and the heart rate starts to come down. Now, when people get older and their brain degenerates, or people get a stroke or they get a brain injury, they lose the skating mechanism. Again, just as if they were kids, they get sometimes dilated pupils or dysautonomia patterns. You can see that in a physical exam. They may get these uncontrolled hypertensive responses. Now, looking at pupils will be a really good clue to you if this is happening. So if you guys are doing a physical exam, and you see someone that has really high blood pressure, right? And they're probably not responding to any of the nutraceuticals, even medication they're taking. Then you put like a pulse ox on their finger, you measure their heart rate, and the heart rate's all over the place, like heart rate variability. Look through pupils, the pupils are dilated, or even worse, the pupils are just bouncing around all over the place, and they're really sensitive to light and sound and those things. Those are all signs that you may have hypertensive mechanisms that are neurogenic in nature. So they're really, really common. And you're going to see a lot of people that have had past high school sports injuries catch up with them. You're going to see a lot of elderly people that have microvascular disease in the brain now having uncontrollable high blood pressure mechanisms that are taking place from that. So it is very, very common, and you need to know about that. Now, for some people, once their brain gets injured or the brain starts to significantly degenerate, these same pathways that control sympathetic tone have an impact on AV and SA node function. So you get altered cardiac electrical circuitry patterns and palpitations and atrial fibrillations. And atrial fibrillations can lead to increased thrombus formation into clots and risks based on how the blood is hitting the heart muscles and how things are in an inefficient mechanism of getting these blood vessels to go through the heart and they kind of accumulate, and platelets get revved up and aggravated by mechanical trauma, and then you can get embolisms that occur. So the risk goes up significantly if people have atrial fibrillation. And for some of these people that have atrial fibrillation and they go in to get surgery done to zap out the bad cells in their heart, but there aren't any bad cells in the heart because it's coming from the brain. So that's a different scenario. And then you have decreased output of the brain to the vagal centers in the lower brains in the vagal areas. And this causes the whole brain to gut axis issue where they have impaired motility and small intestinal bacterial overgrowth patterns and dysbiosis. And then they get leaky gut because they can't get blood flow to the gut, control blood flow, and they get endotoxemia. And if you take a person who has had a brain injury and now they have hypertension issues that are brain-based, now they have vascular injury, gut issues that are brain-based, they may not respond to any of the nutraceuticals that are for the cardiovascular system. You may need to treat their brain function to make some of these changes. We have a few of these cases in the clinical mastership program. If you guys are in that, you'll see throughout the next few modules the next year. But it is pretty common. Okay, let's move on from brain to thyroid and look at some of the research here. So both hypothyroidism and hyperthyroidism can increase cardiovascular risk. So let's talk about both mechanisms. With hypothyroidism, when there's decreased or T3, T4 levels, that impacts the metabolic rate and impacts the metabolic rate of cardiac muscles. So there's impaired cardiac contractibility, there's impaired diastolic function, there's increased vascular resistance, there's increased serum cholesterol. Thyroid hormones also clear out cholesterol from the body. This is when someone's hypothyroid, you see really high cholesterol levels. If you ever see high cholesterol and high TSH, and whatever the cholesterol variations are, like LDL that's high and LDL particle size that's high, but if their TSH is high, you definitely want to have them go on thyroid replacement, see their TSH levels come down, and see if the lipid panel changes. And in many, many cases, it will change. So thyroid hormones are really critical for cholesterol metabolism as well, but they also impact cardiac function. And then if you have too much thyroid hormones, too much T3, T4, that increases metabolic rate, that can cause palpitations, atrial fibrillations, systolic hypertension, congestive heart failure. As a matter of fact, one of the scariest concerns of someone has autoimmune thyroid disease, especially Graves', is they get a thyroid storm. They get such an aggressive release of T3 and T4 that they actually have severe contraction of the muscles and damage their valves. They actually get heart damage from their T3 and T4 levels being too high. Or their T3 and T4 levels are so high, they get fibrillations and hypertension at the same time and they end up with a stroke. So this is the concern for people that have hyperthyroid activity, and especially when they go into a thyroid storm. So let's look at some of these interrelationships as well. T3 and T4 and normal states, normal functions are really important for activating the endothelium. So the vascular endothelial cells have receptor sites for T4 and T3. And T3 and T4 hormones are necessary to keep those endothelial cells functioning well, so it can make things like vascular endothelial growth factor and nitric oxide. You can see these normal responses there. And then thyroid hormones impact lipid metabolism. They control the inflammatory cytokine response, and they have this protective response in the heart. So in longstanding hypothyroid disease, there is increased risk of coronary development, coronary artery atherosclerosis, and systemic atherosclerosis. So this was a systematic review that was published called Thyroid Dysfunction Atherosclerosis, and they conclude that most studies have concluded that thyroid dysfunction is associated with arterial wall remodeling and thus with increased cardiovascular risk. And then if you look at the systematic review, when they looked at atherosclerosis and TSH association based on studies, the 71% of the papers that investigated this found a positive correlation that the higher their TSH levels, the more atherosclerosis they developed. So when you see people that have hypothyroid symptoms for their whole life, and then after 5 or 10 years, someone diagnoses them, then you look at a lab test and no one ran their TSH, and you finally see that they're hypothyroid, those 5 to 10 years where they've been in a hypothyroid state, they've had increased atherosclerosis development. So lots of things can go wrong when someone's in a hypothyroid state for many, many years. We went over that whole list in the Hashimoto's module, but a big part of that mechanism was the impact it has on cardiovascular disease. And someone that has low thyroid hormones for a long period of time is going to have accelerated atherosclerosis. And this is why it's really scary when you see practitioners go, oh, I just have a person's hypothyroid. I'm just going to give them some selenium and see if their TSH goes down. Well, when are you going to check? No, we'll check in here. They feel better. They feel better. Who cares? What does that even mean? Like, what's their TSH? I mean, there's the point, like, you have to do labs and you have to see what these markers are. So, high TSH for extended periods of time is positively correlated with atherosclerosis development. So you've got to get thyroid levels under control. And thyroid hormones directly impact endothelial cells. And thyroid hormones directly impact cholesterol metabolism. And thyroid hormones directly impact cytokine metabolism. Okay, this is a study that was published. It was a meta-analysis, 16 studies, looking at the relation between subclinical thyroid dysfunction and risk of cardiovascular outcomes. And they go on to say that, in summary, our meta-analysis showed that subclinical hypothyroidism is likely associated with an increased risk of coronary heart disease, mortality, and subclinical hyperthyroidism is likely associated with increased risk of coronary heart disease, mortality, and total mortality. So hyper or hypothyroid disease does not only increase atherosclerosis, but the fact that you're going to die from the atherosclerotic disease. Here's a summary of the pathways I put together for you of how T3 and T4 hormones work. So thyroid hormones increase cholesterol clearance by the liver. So they decrease cholesterol and lipoproteins, like HDL, like LDL levels go down, and so forth. HDL levels can even go up. Thyroid hormones increase endothelial nitric oxide synthase, so you get better nitric oxide production and vascular protection. T3 and thyroid hormones impact the mitochondria, cardiac mitochondria, so you have healthy heart contraction, healthy heart metabolism. And thyroid hormones activate the vascular endothelium, promote angiogenesis, so you have healthy vascular branching. So that's another part of the web, is these thyroid relationships. And now let's get into reproductive hormones. And for reproductive hormones, it's pretty simple. When you look at men versus females, in men, when their testosterone levels get declined or become lower, that's when they have significant risk. So low testosterone is the key factor. Now, their low testosterone may be because they're converting it to estrogen. They could have chronic inflammation, which causes the Leydig cells in their testes to not be able to produce testosterone. So they get these andropause patterns. But the point is, if their testosterone levels are low, that does have an impact on vascular dynamics. So this was a meta-analysis study that was published on hypogonadism as a risk factor for cardiovascular disease. And they concluded that lower testosterone and higher estrogen levels correlated with increased risk of cardiovascular disease and cardiovascular mortality. Testosterone replacement therapy and hypogonadism moderates metabolic components associated with cardiovascular risk. Whether low testosterone is just an association with cardiovascular risk or an actual cause and effect relationship awaits further studies, which, of course, like everything. But men will have high estrogen levels with insulin resistance, and men will have low testosterone levels with inflammation. So the testicular Leydig cells that produce testosterone, they have no antioxidant protection. So when there's inflammation in the body, these cells just get injured, and it takes a long time for them to regenerate. So when there's chronic inflammation in men, and it's long-lasting, and it's been going on for a period of time, you can see their testosterone levels totally drop. As their inflammation gets managed, and these Leydig cells start to function again, and testosterone levels can get back up. So one of the most common causes for low testosterone in men is just chronic inflammation. And the most common cause for estrogen level elevations in men is inflammation or insulin upregulating aromatase, where they make these conversions of testosterone to estradiol. And if you look at this meta-analysis forest plot of different clinical trials, you can see that testosterone definitely has a protective effect. Now, in females, it's totally opposite. Let's see, we're still on men here. Yeah, well, this is a study again. This is on testosterone, and basically it shows it helps with glucose, insulin utilization, glucose transport, dampening inflammatory responses. Now, in women, it's totally opposite. So in women, there's a effect on estrogens being protective. And here you can see what's happening with early atherogenesis and established atherosclerosis, but there's decreased expression of estrogen receptor sites. And when you look at the study that was published of 2,838 postmenopausal women over a 2-year prospective study, they found that among postmenopausal women, higher testosterone and lower estrogen ratio was associated with elevated risk for coronary vascular disease, coronary heart disease, and heart failure events. Higher levels of testosterone were associated with increased coronary vascular disease and coronary heart disease, whereas higher estrogen levels were associated with coronary heart disease. The bottom line is it's the opposite effect. In females, high testosterone, which is promoted by, again, insulin. Insulin activates the 1720 lyase. That increases cardiovascular. So women in postmenopause need, some of those. Women in menopause need to have high estrogen, higher or normal estrogen levels, and lower testosterone. This is the summary of the endocrine pathways. So decreased testosterone in men, or decreased estrogen in women. If you really look at the mechanisms, increases cell wall adhesions in blood vessels, increases vascular inflammation, increases plaque instability, increases vascular oxidation of LDL, decreases endothelial nitric oxide, and decreases vasodilation, all the things you don't want. So hormones do play a role in this web, and ultimately the relationship between the gut, thyroid health, hormones, how active white fat cells are versus gray fat cells, insulin resistance, insulin factors, and brain function, all are upstream mechanisms that have a role in vascular health. So I hope that was useful for you.